this session will be recorded right now with regards to friction. Okay, so if you have questions, I'd say just type it out, unless if you want your voice as part of the recording. Again, as usual, out of courtesy, make sure your mics are muted so that we don't hear all the background noises. All right, so this block we're going to be talking about friction and what exactly is friction. All right. Now, in a grade 11 textbook, they'll just tell you this. Friction is a force produced from a contact between two smooth surfaces, which is opposite in direction of motion. And you're probably used to this idea about friction, right? Let's say you have a type top like this up here, and you place something on top, like, I don't know, this fire truck over here. All right. As I'm pushing this fire truck towards you, unfortunately, because the wheels are not perfect, I feel this drag, and the drag will be in the opposite direction. After all, if this drag didn't exist, then the moment I push this, then the inertia of this should carry all the way towards my face, but it doesn't, all right? And because there is internal friction in this. I think it's more apparent if I hold this fire truck like this, okay? So as I push this fire truck towards your right, the force of friction will fight in the opposite direction, which is on the other way. And if I push this fire truck on this way, the friction will oppose in the opposite direction. Yes, this is more of that of an European fire truck. Also, it's more than meets the eye, if you know the reference. Okay, so that's the grade 11 answer, but I also want to share with you the grade 13 answer, I guess the first year university answer, which says this. On a microscopic level, friction and normal forces result from the intermolecular forces between two surfaces at points where they come into contact. The actual area of contact is usually much smaller than the total surface area. As a box slides over the floor, bonds between the two surfaces form and break, and the total number of such bonds varies. Hence, the kinetic friction is not perfectly constant. All right, again, this is from a first-year university textbook, so I know it looks weird. The idea I want you to get out of this is that friction, fundamentally, is electrical in nature. All right, and what does that exactly mean? Well, remember that all material out there in the universe is all made up of atoms. Atoms have protons, neutrons, and electrons. So that's where that whole electrical in nature is. In other words, one atom has an inherent relationship with another atom in the distance, and that's because they're electrically in love with each other. All right, so one that's more positive falls in love with one that is neutral or slightly negative. All right, and that's what initially generates friction. A lot of people think that friction is caused because you have the treads in your tire or the treads on the shoes on the soles of your shoes. And really, that's not friction anymore. That is traction, all right? That's deformation of a surface so that it falls into the molds of the second object, therefore making one solid entity, and you're slowly destroying and disintegrating one of them as you move them across. That's why tires wear down, okay? And we're not talking about that in this grade 11 friction definition. We're talking about the fact that as long as you have any two smooth surfaces, even paper on top of paper, you'll notice that when you rub them on top of each other, there is this grit that holds them back from moving. And again, it has to do with the electrical bonds with each other. Okay, so that's what friction is. It's this weak electrical bond between two surfaces that inhibit motion. All right, and through doing thousands of experiments, this is what scientists have noticed, that the relationship between the numerical value of friction measured in newtons is proportionate to whatever the normal force is of the object. That's what they've discovered. In other words, they have this generic formula. Force of friction is proportionate to Fn. All right, remember that alpha, it's just simply means it's a relationship. In other words, if you double the normal force, the frictional forces will double. If you triple the normal force, the frictional forces will also triple. All right. Now, there might be a multiplier in front of it as well, so it might be even more significant or less significant, but we know that it's going to be this proportionate ratio. One increases, the other one will also increase as well. Okay. So we probably have a letter K in front of it. But for friction, we don't use the letter K like in yesterday's lesson. Instead, we use the letter mu-s or mu-k. Okay. So that's the new letter for today. Mu. It's another Greek letter, and this is the coefficient of friction. There are lookup tables that tell you these values here. Okay, what do you need to copy down your notes? Everything up to here is sufficient. You don't need to jot down anything beyond what you see here. Okay. As for the value of mu-s, it can be solved experimentally, and I'll tell you afterwards how you can determine that value. It's not that difficult. However, since that value is going to be consistent, in other words, if it's paper on paper, I expect a certain coefficient. All right, so if it's paper on paper, I expect a certain coefficient. If it's paper on top of a drawing board, I expect it to be another value because the drawing board is a bit smoother than paper. And so it's a relationship between two separate surfaces, and that number is more or less a constant. All right, and that's why you can find out that constant on lookup tables. According to your textbook, you can find it on page 170, but you can also Google this as well. So if you go onto the internet and you type in coefficient of friction, you'll see that there are pages and pages of coefficients of friction. Okay, so again, I'll give you guys a moment just to jot down the text that's in blue that's important. Sorry, the text that's in black is important. As for the text that's in blue, no, you don't necessarily have to copy that down. We're going to spend most of our time on the equation on the right, okay? Force of friction is equal to mu k times Fm. As for the equation on the left, we'll briefly touch it here and there. Mu s is focused in more detail in grade 12 physics. Okay, so in grade 12, we will revisit this concept again, and we'll cover it in more detail, especially, you know, when you park your car uphill. What's holding it up there? Like the family of Peppa the Pig, right? How does our car, how is it able to go up that hill? Well, there has to be a certain relationship between the tire and the ground for them to make it up there. In fact, that's a great example that I want to go through right now. It's a great segue, okay? Because often enough, we care about friction because we care about the relationship between the rubber on your tires of your car versus the contact it makes with the ground. Now, in the lookup table in your textbook, it describes concrete, but you can also imagine it as asphalt as well. I'm sure the numbers are similar, not exact, but they are similar in pattern, okay? And you would expect that the reason why we choose to use rubber for our cars is for one of two things, all right? For one thing, it's of comfort because it's air-filled, so it's able to absorb a lot of shock on the ground. But number two, we know that rubber and concrete, there's a high coefficient of friction, and we want that. In fact, if you look it up, what the relationship is, the value is at 1.0, all right? And that's when they are static to each other. That's one of the common misconceptions we have. Do I have a tire around here? I don't have any wheels. I wish I had a wheel around. Oh, I have something that looks like a wheel. I know this will be one of the world's loudest wheels, but this is something that's circular, all right? So here's a question, all right? As this wheel is moving on top of this ground over here, is the relationship between the tire and the ground static, or is it kinetic? Remember, the kinetic is in motion with each other. I probably could put up a poll right now, and I think a lot of people accidentally will write down what someone just typed in, okay, which is not the correct answer. And here's the weird thing about it, okay? Kinetic friction is a relationship when the two surfaces are rubbing with one another. For example, this paper on top of this slate. This is kinetic friction. Static friction is when the two surfaces are stationary to each other. I know there's the illusion that the tire right now is sliding on top of this slate. However, it's not sliding on top of this slate. If you look closely between the two surfaces, they are making a static contact with each other. Okay, so they're not gliding on top of each other. They are making a static contact. So on an ordinary day, when you're driving your vehicle, the coefficient of friction between your car's tires and the ground will be at 1.0. Okay. Now, if you had to slam on your brakes because you see a squirrel on the road and you want to spare its life, then you'll start to hear the screech sound. And this is when the two surfaces are rubbing on top of each other. All right. So now you've switched over to a different type of friction, which is kinetic friction. Okay. So once again, static friction is when the two surfaces are stationary relative to each other, and kinetic friction is when they are in motion with each other, and the values will decrease. Okay, so I think that's another question. Why does the value decrease when they're in motion with each other? I guess I'll use my hands to explain what's going on, okay? We know that there is friction between my two hands, and right now you'll see that they are relatively stuck with each other, okay? And they're stuck because they had a chance just to hang out with each other, and they're able to form these weak electromagnetic bonds with one another, okay? And that's why they're stuck with each other. But the moment I end up pushing one with each other relative to the other one, now the bonds will break, and there's not enough time for them to rebond and form that solid bond again. Normally, a demonstration I do in the classroom is that I have a ramp elevated at some predetermined angle that I measured earlier. I place an object on top, and you'll notice that as long as I leave them stationary to each other, they won't move. But the moment I move that first object, the second object will just keep on gliding downwards because it doesn't have time to bond with each other anymore. Again, I have not changed the elevation of my ramp. I left it exactly the same. But the moment I started letting it move, unfortunately, I broke those bonds and they started gliding. And that's why when you look at this lookup table over here, the coefficient of kinetic friction will always be less than the coefficient of static friction. That is always going to be a trend. Now, Amelia has a question. Just remember that you're being recorded right now for your question. Please ask.
So can you repeat what the difference between static and kinetic is?
Certainly. Kinetic friction is when the two surfaces are rubbing with each other. All right. So again, when this TV remote is gliding on top of this slate, this is kinetic friction. Static friction is if you give it a moment in time, there's no numerical value, but you can imagine as, a fraction of a second, where they have a chance to bond their molecules together. And once they do, they remain static with each other. So this is static friction over here. Again, a classic high school demonstration that we do, and it probably works better on this slide, is that I'll carefully place my object and I'll pause it on a certain spot on this slate. Okay, and you'll see that it's not moving. And that's because it's given enough time to bond the molecules each other electrically. Okay, not chemically, but electrically. However, the moment I give this a slight little jerk, you'll see that it does, where's the critical angle? Somewhere over here, okay? If I give it just a little push, I've gone beyond that critical threshold, and no matter what I do, it'll just keep on sliding, okay? And that's because as this remote is gliding on top of the slate, it's not giving enough time for the two molecules to electrically bond together. And that's why the values will decrease, all right?
Okay, thank you.
So that's the general summary here. We'll find out that the coefficient of static friction in general will be higher than the coefficient of kinetic friction. Okay, and this problem becomes even more apparent if we have some form of lubrication between the two. Not that we're relating that in grade 11, but that great example does exist in this slide over here. Okay, this is an example where first off, the two surfaces are dry with each other, so we don't have a lubricant, and these are the numerical values. All right, on a rainy day, the values we would expect it to decrease, and that's the concern about when there's snow and slush outside when you're driving. All right, your coefficient of friction decreases, so your chances of going out of control increase. Can there be both static and kinetic friction applied at the same time? No, we are either in one state or in the other. So in other words, either we had, a 100th of a second, let's say, again, there's no specific number, but we had a fraction of a second for them to say hello to each other and bond, or they don't have time at all because they're just constantly in motion with each other. Okay, so the object is either static to the surface, and then you use the higher number, or they're in motion relative to each other, and you would use the lower numerical value. One more thing to point out is that you'll see that this is described as static coefficient. And just like in math class, you know that a coefficient is just a number that you place in front of another number. That's all we're doing here. All right. So for example, we're placing this cast iron on top of copper. We're going to sub it in to that spot over there. The reason why I'm telling you this is because the coefficient of friction is unitless. All right. In your mind, and this is how I think about it, I think about it as a percentage. All right. So for example, with regards to the car on top of dry concrete or dry asphalt, all right, the coefficient of friction is at 1.0. In other words, whatever the normal force is, that's exactly your force of friction. And on a rainy day, you can see that the force of friction has decreased by about 3 times. Now you're only approximately 1/3 for your force of friction on a rainy day. And that's why your chances of driving out of control increase on a rainy or snowy day. And what makes things even worse is what if you start skidding? Because you can see the values decrease even more. And that's why in modern vehicles, they have this thing called ABS, or anti-lock braking system. All right, where behind your disc brakes and your caliper, which is the guy over here. So you got your disc brake, you got your caliper, you have this funny looking spokey thing. And that spokey thing, no, it is not a gear. All right, all it is that's a presence of metal, or it's carved out so there's no metal. Whenever we have sensors, we never want sensors to physically rub on top of each other because that's going to generate friction. So instead, they use a different technology, which is called a Hall effect sensor. In other words, it's a sensor that's kind of like a metal detector. It's detecting either for the presence of the spoke or that air gap in between. All right, that way there's no physical contact between the sensor and the rotating wheel system. And the way how the ABS system works is that there's a sensor for each of the 4 wheels on your car. And when you slam on your brakes on a day where the ground is slightly slippery, it's going to see and calculate out the rate of deceleration of all four wheels. If one of the wheels happens to decelerate far faster than the others, then there's a good chance it's going to slip over from static friction into kinetic friction, and then your car is going to spin out of control. So what it's going to do is it's going to quickly release all the other brakes from the three remaining wheels so that all the wheels decelerate at the same rate. And that's how your whole traction control of your vehicle works, all right, with the anti-lock braking system. That's how you're able to stop in a straight line as opposed to spin out of control. All right, so one question over here. The lower the coefficient of friction, the higher the chance of slipping over. Yeah, I guess you can think about it that way, okay? Or slipping, period. Not slipping over, but just slipping. So in other words, if you place butter on your pan when you're cooking, your coefficient of friction should be rather low. Okay, and that's why if you use cooking plates like Teflon, or if you slide Teflon, would you expect the number to be rather large, or would you expect the number to be rather small? Good, rather small. Here it is. Yes, student, you have a question?
Just to clarify, so when you're driving a car and it's moving on the road, and it's just driving normally, that would be static because it's not rubbing against the road.
Yeah.
And if you're braking, since it's rubbing against the road, it would be kinetic.
If you're braking and it's rubbing because you're doing a Tokyo drift, like on your bicycle, then that's kinetic friction. All right. So if you're drifting, yes, you are, but you never want to be in kinetic when you're braking because your car may go out of control.
Okay.
Makes sense? So you want your wheels to not skid on top of the ground. Now that's why you'll see skid marks. You want it that when you decelerate, that your tire is constantly making contact, whether if you're speeding up or if you're slowing down. All right, okay, so you want to be under the circumstance of static friction throughout your entire drive, unless if you're a stunt driver. Okay, any other questions, guys? Okay, so again, these numbers over here, they will be part of a lookup table, so you're not expected to memorize any of them. I'll just tell you that there's a story about, a box sliding on top of carpet, and the coefficient of friction is some number, all right? And then you'll just be using that number in solving your problem. Okay, so this table you don't need to memorize. I think what you should know in general is that, yes, static friction in general is greater than kinetic friction. And some of you eagle eyes might be wondering, well, why are these two numbers the same? Well, remember, when you're looking at those numbers over there, they're only one sig fig. For all we know, the second number over here could have been 0.038, but it was rounded up to 0.4 because that's how the author listed it here. Okay, so we would expect the coefficient of kinetic friction to be less than static friction. It's just that these numbers here are an approximation. And that's, I think, one important thing of why I kept that blue text up there. Okay, it's approximately proportional. And that's why these measurements over here for coefficient of friction, they're only 1 or 2 significant figures, all right? Again, this one's only 3 sig fig because it's just 1.05. But in general, we don't really list them as 3 significant figure numbers, all right? We normally list them either as 1 significant figure or 2 because it's just an approximate answer. We don't expect it to be spot on. Okay, there was a video that I was supposed to share with you. Again, this video has been posted in Google Classroom, so you can watch that afterwards. All right, and it's a bunch of researchers that take advantage of knowing what friction is and try to see that if you can find a safer shoe out there. In fact, in their research, at the end of the day, what they're really trying to find out is find a shoe that has a softer sole. That way you improve its traction because the sole itself is able to mold into the contour of the soil or of the ground, thereby creating better grip. All right, so you're not in the world of friction anymore. You're moving on to the world of traction. Okay, things to keep in mind when you're solving these problems here. All right, I know this sounds weird, but surface area has absolutely no impact in your final answer. Okay, so let me just pull out a rectangular box over here. Okay, so I have a lovely rectangular box. Sweet, found a spare screwdriver. Okay, so I have this box here, and we know that's cardboard, cardboard, cardboard. I'm going to rub this cardboard on top of a plastic slate. Funny enough, if I try to find out the coefficient of friction, if I measure it over here versus if I measure it over here like this, or if I measure it vertically like this, my answer for that force of friction is going to be the same exact answer. All right, so that's our first consideration. The surface area of the object does not impact its frictional force. And if you're wondering about, why that is true, well, it has to do with regards to the distribution of this normal force. All right. When I stack this block upwards like this, we notice that the surface area is rather small, but also it's applying all that force into that smaller contact area. All right. On the other hand, when I drop it out like this, it's spreading out the forces over a larger surface area. Okay. So in other words, those two effects are canceling each other out. So even though the pressure is higher here, the surface area is smaller. Here, the pressure area is lower, but the surface area is greater. So those aspects of it cancel out, so we don't care about surface area, right? And that's why in the problems that are listed in tonight's homework, there's no description about how big the object is. It doesn't matter in our final answer. As a reminder for point number 2, make sure you know when to use mu k and when to use mu s, all right? When I'm sliding this box on top of the slate, this is mu k. If I'm sliding the slate on top of the box, this is still mu k because they're moving relative to each other. All right. On the other hand, this is an example of mu s, and while they're moving like this is still mu s. So even though you may be observing the slate and the box moving right now, they are stationary to each other. All right. So those are other things to keep in mind. Okay. And yes, it is far easier to push objects when they're in motion. Remember that mu s is greater than mu k. You might have experienced this when you're trying to push, for example, your couch in your living room. At first, you have to give it a huge shove just to break the contact bonds between the feet of your sofa and the ground itself. And after it's in motion, it's pretty easy to move until you get too tired and then you cause the sofa to stop. Then you realize that, oh man, I got to put in more effort in giving it that shove at the beginning again just to get it started to move afterwards. Okay, so I hope that you've experienced consideration number 3. Okay, I think right now is a good time for me just to draw out a picture to tell you how would you find out what the value of mu k is. It's actually not that hard. What you'll need to have is something known as a Newtonometer, which is a scale. I can't find mine here right now, but you can imagine that if I place the scale on this, the force of gravity will be pulling down on this box. And as long as I keep everything static, what the spring will measure is the tension or the force holding this box up so it doesn't move. So the force of gravity will match up with the force of tension, and that's how I'm able to find out the weight of this box. Okay, so the Fg of any object can easily be found by using this Newtonometer. Okay, so Fg is determinable. Okay, by just hanging the mass on top of a scale. Done. Another thing that's attainable is by placing the mass on top of a surface, and then I drag it at a constant velocity. Remember, if I drag this at a constant velocity, acceleration must be at what? If f is constant, then acceleration is equal to 0 meters per second squared. And if you take a look at F net, if it's equal to ma, if a goes to 0, then F net also goes to 0. Okay, here's the next part. Let me finish off with the free body diagram over here. Okay, so we have our normal force, we have our force of gravity, I have my force applied that I'm pulling it at, and the force of friction, which is fighting backwards. So if my F net is equal to 0, what that tells me is that the force I apply minus the force of friction is equal to 0, or the force that I apply at is equal to the force of friction. So what I'm going to do is I'm going to take that scale, I'm going to clip it onto the end of this box, and I'm going to drag it. And while I drag it at a constant velocity, I'll measure a numerical value. Okay, so it is possible to measure the force applied. Don't worry, new friend. This is being recorded right now, so you are able to watch it afterwards. Okay, so now we figured out what the Fg is of the object by hanging on the scale. And then when I drag this across, I can find out the force that's applied. All right, and as we know, as I'm dragging it at a constant velocity, the force applied will be equal to the force of friction. So now I have a known value for Fg and Ff, whatever they are in my experiment. Now, if you look at the formula, force of friction is equal to mu k Fn. Well, to solve for mu k, all I need to do is I need to divide, Ff by Fn. Okay. And we've figured that out, right? The force of gravity, again, in the vertical dimension, is equal to the normal force. So Fg is equal to Fm when I'm just suspending it. So we do know Fn. All right, so now that we know the Fn, we know the force of friction, we can solve for mu k. Okay, so that's how you can find out the force of friction of an object, just by taking a scale and dragging it at a constant velocity. So yes, I assume that, yeah, you do have to have at least one measuring device to figure out the force of friction, but it is a doable lab at home if you have that scale. There is a plan B, and that plan B is in diagonal ramp. All right, but for more adventures of that, make sure you like, click, and subscribe to grade 12 physics, where that will be described. So there's another way to find out the force of friction without using any technology at all. All you need is just a ramp and a ruler, and that's it. Okay, but I'm giving you the grade 11 approach. Use a Newtonometer, and you can find out the force of friction. And if you want to find out the force of static friction, what you're going to do is that you're going to drag on the box with your scale until it starts to move. Remember, as we mentioned, objects will form this strong bond with other objects electrostatically. So in other words, you need to have a bit more of a tug force before it starts to move. And that's what you're going to do. You're going to apply a force, and you're going to see the scale as the numbers grow, grow, grow. And once it reaches its highest value before it decreases, you'll take that as your force of friction. And you'll divide that by your normal force. And since you require more effort for this, your force of friction value will be a bigger number. And a bigger number divided by your normal force, which is the same, will give you a larger mu(s). Okay, so I hope that you are able to understand that. That's how you'd figure out these numbers here if you wanted to. Again, for us, we don't need to figure that out. It will be given to you on any quiz, test, or exam. And again, if you look it up on the internet, just type in coefficient of friction lookup table of friction table, and look at that. Tons and tons of table, and this is what scientists do for a living, okay? They will just drag one object on top of another object and find out what the coefficient of friction is. That's the entire experiment. What do you not need to know the numbers? No, as I mentioned, you don't need to know any of the numbers. I will give it to you on the test. I'll give it to you on a lookup table. And that's it. Even easier, for the most part, I don't even give a lookup table. I'll just say it right in the question. Assume in this question, mu k's is 0.12. Okay, just to cut to the chase. Any other questions before I move on? Remember that you're being recorded. What is your question?
So because A is equal to 0 because it's constant, why is F net 0 also?
Okay, good question. How would I deal with this in color, and then it'll make a bit more sense? Because right now we're seeing a bunch of blue lines everywhere, and I think that's where some of the confusion comes into play. Okay, we're talking about F net in two separate dimensions, where we're trying to aim for both of them to be at 0. Okay, in fact, let me just erase everything so I can start from a clean slate. Okay, I have a mass. I have my normal force pulling upwards, the force of gravity pulling downwards. I have a force, I'll call it Fa for my applied force, and then I have my force of friction. To finish off this free body diagram, I'm going to include a coordinate system. We always assume that the force of friction opposes the direction of motion. That's why I'm assuming right is positive, all right, if friction is going to be the other way. And just for standard convention, we just usually say that upwards is positive. Will it really matter? No, not really, because you know that your F nets are aiming to be 0, so it doesn't really matter what you define. Okay, but let's just stick with these standard conventions. So as I said, in the vertical dimension, as long as the surface is flat, we know that the normal force will match up with the force of gravity. Okay, so we deal with our F net in our y dimension first. So F net y is equal to Fn minus Fg. Again, we see that the box isn't flying off into the air. It's not sinking into the surface. So we know that F net in the y dimension has to be 0. Therefore, our normal force is equal to the force of gravity. That's one thing that we know. Do we need to know that right now? No, but I'm just letting you know that that is true. That is 0. Another thing is 0 as well, your F net in your x dimension. Again, I'm taking this box and I'm dragging it at a constant velocity. So if I'm dragging it at a constant velocity, so if v is constant, you know that A is equal to 0 meters per second squared, right? Because when you're moving in a uniform motion, you're not accelerating, you're not decelerating. Another thing that is true is Newton's law. F net is equal to ma. So if A is equal to 0, well, any number multiplied by 0, so it doesn't matter how much mass you have here or how little mass you have here, if the acceleration is at 0, then we know that F net in this x dimension is also equal to 0 newtons. Okay? All right. So why are we doing that for this problem here? Again, we're trying to solve for the force of friction, and this is the little life hack. Okay, our F net in our x dimension, well, it's on the left. Our F net in our x dimension is equal to the force applied subtract the force of friction. So as long as we're careful enough to drag this box and not let it speed up and not let it slow down, our F net x will go to 0. In other words, the force that you apply dragging it forwards will match up with the force of friction backwards. So if you had a Newtonometer to measure your force applied, you've automatically found out your force of friction. That's the hack in solving it. So we do not need to know that. I'm not sure what you not need to know, but I'm telling you the science of how this thing operates. And by understanding how this thing operates, hopefully we can start answering all the questions in our homework. So it's more of an overall idea just to keep in the back of your mind than anything else. Because in one of your homework questions, it's going to ask you, you have a lawnmower and you're pulling the lawnmower. What force must you push it at so you can overcome the frictional forces and cause the lawnmower to move at a constant velocity? In that case, you want your F net x to be equal to 0. So even though you may not need to know this question per se, understanding the concept of what 0 implies, you will need to know that. I hear a bunch of clicks up and down. So are there any other questions before I advance on? Yes.
Why is A equal to 0?
If we assume that V is constant. Remember, the experiment, I said, what I want to do to make this value measurable. So if I want to find out what mu k is, one thing I have to do is I need to drag this at a constant velocity. In fact, that's a reality with a lot of what we do in solving problems in this world. We use life hacks in solving it. I know this may sound crazy, but if you need to figure out how a plane is able to spin itself like a F-14, so you know its moment of inertia, what do? They suspend it on pieces of string, and then they just give it a quick little wobble, and they look at its rate of resonance, okay, the amount of times that it resonates back and forth like a pendulum. By counting out its torsional measurements, you can figure out its moment of inertia when it rotates. Right? So it's a very hard number to calculate out because an airplane is so big and there's so many things moving around. But by using these simple little hacks, if you know the details of how to do the numbers, you can do a very simple experiment to find out the answer. There is this other cool one, which is, well, if you know that a scale works because of gravity here on Earth, how do you find out the mass of an object when you're in outer space? That's a life hack as well. And the answer to that life hack will be covered in grade 12 physics. So stay tuned for that episode. Any other questions, guys, before we move on? So I hope they've appreciated, so far, I know they're going through things very quickly, that, there are patterns that we notice. All right, and these patterns can allow us to predict the outcome of things. Again, with regards to projectile motion, I know that we weren't able to do a demonstration with each other using this medium, but if you were to do the experiment with a projectile launcher, it will land within 10 centimeters of your target because that's how well calibrated those launchers are in high school. I do have a YouTube video on it, so please, if you haven't had a chance to watch it yet, make sure you watch it just so you can appreciate that the math does work out. It does. It's just that it's better that you can appreciate it when you can have that tangible object in front of you to witness it and see in motion. Stay tuned. One of your assignments, it will be like that. All right. So if you guys haven't done so already, make sure you guys start hoarding up on these things over here. Okay. So if you have toilet paper rolls around or even tissue paper rolls around, keep them around because we're going to be doing physics with this in the comfort of your own home. And you're going to see that the theory does work out with the real life outcome. Okay. So start hoarding up on toilet paper rolls or tissue paper rolls or gift wrap rolls. Any roll will do. Okay, I do need to move on so I can get through my lesson. All right, so we've talked about what friction is, how you can determine the number. Again, I'm not going to expect you to figure out that number. I'll just give that value to you because we're going to use that number to figure out the overall outcome of an object. All right, so yesterday we had this problem here specifically. Okay, I just want to reuse yesterday's lesson so that we have a reference number. A hand is pulling against a box with a force of 5 newtons to the right. If you look at your F net in this problem over here, we see that our F net y goes to 0 because the box doesn't sink to the ground, it doesn't fly into the sky. So our F net is just equal to FH. And if we know that acceleration is our F net divided by mass, then 5 newtons divided by 2 kilograms will give you 2.5 meters per second squared. So that's why you'll have that number listed on top. That is our reference number. That's it. Okay, so we're going to keep that reference number up there so that we can see what happens to acceleration the moment you turn on friction. Okay, so this time around, we're not on a air table or an air hockey table. Now this is a physical object, but it's gliding on top of wax paper. All right, so it still has the mobility to move. Unfortunately, that coefficient of friction is a numerical value. Roughly 12% of your normal force attributes to friction. One problem about the force of friction formula is that it's always written like this. Ff is equal to mu k times Fn. Remember that forces are vectors. But if you look at the formula over here, you'll see that the arrows are missing. And the reason why the arrows are missing is that if you end up placing an arrow on top over here and on top of here, you're telling the reader that the normal force, which is going up and down, is the same as the direction of friction, going up and down as well. And that doesn't make any sense. If I take this box over here and I drag it towards the right, we know the force of friction is towards the left. If I drag this box towards you, the force of friction is pointing towards me. And that's why we have to get rid of those arrows on top. All right. In some textbooks, what they'll do is that they'll go nerdy and they'll do this whole business over here. And as you know, we don't need to write down all of that because by getting rid of the absolute value and the arrow on top, we're already telling the reader that we only know a scalar answer. Okay, so here's the thing where you need to have a bit of human intuition in solving the last part of this free body diagram. It's not complete yet. If I'm pulling an object towards the right, we know intuitively that the force of friction must be moving which way? Good, towards the left. And there you have it. There is our free body diagram. All right. So the force of friction is something that you need to insert as a human being by looking at your circumstances. If you see the accelerate system moving towards the right, friction's to the left. If the system's moving to the left, then the friction is moving towards the right. All right. So that's the bit of human intuition right there. All right. Now that we have the free body diagram completed, now let's start solving this problem. And yeah, I'll solve this problem with you real time. It is pre-animated out, but maybe it does help if I just tell you what's happening each step of the way. All right. That we have a better understanding of what's going on over here. Okay, so we need to solve for the force of friction, and as you may know, to solve for the force of friction, you need to use this formula here. And to use that formula over here, well, you have no choice but to solve for your Fn. All right, so by that logic alone, your first step in solving all these problems is not to solve for F net x. Instead, it is to solve for your F net in your y dimension. That's step number one. Solve for your F net y. Okay, so again, this is the object that's gliding back and forth, right? It's not going up or down. So what do we know about F net y? It is equal to 0. Good. All right. So we know that F net y has to go to 0. That's the symbolic notation to tell the reader that this value over here goes to 0. And the reason why it's going to go to 0 is because these two forces will fight out with each other. Okay, you have this normal force, which is pushing upwards by the table itself, and you have gravity that's dragging it downwards. So minus Fg. Remember, I did insert a minus sign in here, okay, to tell the reader that I am going in the south direction. No, not south, in the downwards direction. Okay, so since F net y is equal to 0, what this will tell us in this simple problem is that our normal force is equal to Fg. And if you recall from yesterday, Fg, if you want to solve it, that's equal to mass times the gravitational field strength here on Earth. Okay, so in other words, Fn is equal to mg. This has a mass of 2 kilograms. We're going to multiply it by the gravitational field strength here on Earth of 9.81 meters per second squared. And again, a meter per second squared has the same meaning as a Newton per kilogram. You don't have to replace it, but how about I replace this so that you can better appreciate why I am doing that. That way we can ensure that the kilograms in the numerator will divide out with the kilograms in the denominator and find out that our normal force is at 19.62 newtons. That's our normal force. We've also discussed the fact that scientists have discovered that our force of friction is proportionate to our normal force. So as our normal force increases, our force of friction increases as well. If our normal force drops, then the force of friction drops also. There was a question about the minus sign. I want to clarify that minus sign afterwards. All right. I know that's a common thing. People are wondering, why am I not putting a minus sign up here? Let me explain that afterwards. Okay, I'll explain that afterwards. In fact, the hint is this. That's the reason why. You've already done it. Okay, you've already done it. But I'll explain that afterwards. Okay. In fact, I'll erase this all over again, and I'll show you version B, which is the actual version A, but it makes it even more confusing. Do that afterwards. Let's go through the standard way that you'd solve this normally. Okay. Force of friction is equal to mu k, which is at 0.12 times your normal force that we just solved for, of 19.62 newtons. For this, I'll need a calculator. Can't do that in my head. And we get 2.35 newtons. Okay, and remember, this is the value attributed to the force of friction over here. Now let's solve for our F net in our x dimension. Okay, F net in our x dimension. F net x is equal to, we deem right as positive, so it's the force of the hand subtract the force of friction. The force of the hand is at 5.0 newtons towards the right, and the force of friction is at 2.35 newtons. Whoops, I don't need to write right. It's already implied that. All right, and the force of friction is backwards at minus 2.35. So 5 newtons subtract 2.35 gives us 2.65 newtons. Again, since F net y is equal to 0, there is no need for the Pythagorean theorem. All right, so we know that our F net is just equal to F net x. That's what I'm trying to get at. Okay. All right. Now, we also know that F net is equal to MA, right? F net is equal to MA. I'm doing that so that we can figure out the acceleration of this block now. A is equal to our F net divided by mass. Again, our F net is just our 2.65 newtons towards the right and nothing else, because that's our net force. Vertically, it's at 0. And right now, the force of the hand is winning. And the mass of 2.0 kilograms gives us an acceleration of 1.325 meters per second squared towards the right. With our givens of 2 sig fig, the appropriate answer for this is 1.3 meters per second squared right. And that is our final answer. Okay, and again, this is the way how we would solve this on any quiz, test, or exam, because this is easier. This is the one where we go from vector to scalar, and then we go back to vector again. Okay, now let me answer this whole question again from a different approach, and then you'll have a better appreciation of why we're doing what we're doing. Okay, some people were asking, wait, sir, why didn't you put negative 9.81 over here? And the reason why I didn't put the negative 9.81 over there is because I've already forced that card on you, like playing card decks, and I'm forcing that card. Okay, I've already told the reader that the force of gravity is downwards. So why are you putting the minus sign again? You're going to double negative it, as some people have implied. That's one reason. Okay, and let me just show you the proper way of solving these things, but it's the long way. And if you want to solve it the long way on a test, by all means, but it's painful. So here we go. I'm wiping out everything, and let's solve everything grammatically correct right from the beginning. Again, F net, just keep this in mind, that by definition, F net is the sigma of F, or the sum of all forces. That is the proper definition as a vector. Okay, and vectors, as you know, to get to your answer, you always add. That's what you're also always supposed to do. So let's rinse and repeat solving this as a vector, right? So F net y as a vector, by definition, is the sum of all vectors in the vertical dimension, which is Fn plus Fg, because that's the proper definition of it. Okay? Now, we know that our F net y is going to go to 0 because, again, it's not going to fly up into the sky. It's not going to sink down into the ground. So our Fn is equal to negative Fg. So there's a minus sign. That's okay. And what is Fg? Well, Fg is equal to m times g. In other words, negative mass of 2.0 kilograms times, well, I will even use the negative sign. I'll just use the proper one, which is 9.81 meters per second squared down. All right, and I hope that by seeing it this way, that down times that negative will give you a normal force of 19.62 newtons up, which is true. The normal force does point upwards. Again, we can solve the rest of this problem, this method, for posterity's sake, since this is recorded, I'll go through that trouble so that you can see that the math does work out. Again, this is rather convoluted, and it's just so much extra work, but hey, it will work out. As I said, that's one of the beauties of physics. The math always works out. Okay? Again, F net x, by definition, is equal to the sum of all forces. So the sum of the force of the hand plus the force of friction plus whatever forces you have to the left or to the right of you. Now, the force of the hand is at, what's it, 5.0 newtons towards the right. Again, the force of friction, we know that it has to go in the opposite direction. Oh, I forgot to do that calculation. Oh, well, I know that you guys know how to do this by now. F of F is equal to mu k times Fn. And, you know, here's where vectors start falling apart, because the proper formula is absolute value. Because the formula can't tell you the direction, you have to intuitively solve that as a human being. So 0.12 times the scalar of 19.62 newtons will give you 19.62 times 0.12 will give you 2.3544. All right, so it only tells you the absolute value. You need to know as a human being that according to this diagram, your force of friction is technically 2.3544 newtons towards the left. And that's what we're going to do. 5 newtons to the right plus 2.3544 newtons to the left, which, hey, unless the vectors are of the same direction, you can't add them. So we have to do that quick little hack where we got to change one of the two. So 5 newtons to the right minus 2.35 newtons towards the right will give you a net value of 2.6456 newtons towards the right. Okay, and since our F net y is equal to 0, we know that acceleration is just equal to F net x as a vector divided by mass. All right, and here's one interesting thing. Math always works out, even with regards to vectors. Whenever you divide a vector, 2.6456 newtons towards the right, divided by a scalar quantity, such as 2 kilograms, you'll notice that a vector divided by a scalar will always give you a vector answer. It is a true property in mathematics. Something that, again, just to simplify this course, I don't say these things out loud, but now you know. Right, 1.3 meters per second squared towards the right. So a vector divided by scalar still gives you a vector. A vector times a scalar will give you a vector, and a vector times a vector, you're going to the third dimension. More of that in grade 12 math. Okay, so again, the answers for all of this stuff over here, it is available in the PowerPoint. So please, if you want to look at it over here, that's just another way of approaching towards it, which will arrive to the same answer. Okay? All right. Now, let's move on to questions that I'll probably give to you on a quiz, test, or exam, all right? Because I always start off with the simplest one so that you understand the foundation of it. So let's move on to one that's slightly more challenging. Because the reality is that you are dealing with forces that don't always play so cleanly, like in the X dimension, in the Y dimension. Often, you know, for example, when you're pushing a lawnmower, you're not pushing it forwards, you're pushing the lawnmower downwards into the ground. All right. So often you're pushing with a force angled downwards. Now I'm giving you a very similar question as before. All right. In yesterday's lesson, we had a question that looked kind of like this. Somebody's pulling down at a diagonal. So this force of the applied hand has two components. It has a horizontal component and it has a vertical component. Okay. All right. So, yes, there's a lot of things going on in physics. It is a intense and challenging course. Okay, one thing that you have to think of intuitively in solving this is the force of friction. So look at this picture over here. Which way will the force of friction point, logically? Remember that this is on top of a surface.
Left.
Good. The force of friction will be pointing towards the left. That's something that intuitively you have to figure out on your own. And this is it for a free body diagram. All right. In general, we don't break it down into its components. But just for our sake, for our learning purposes, let's just dot these out so that we can see when to use one angle and when to use the other angle. Remember that the problem says downwards 30 degrees towards the right. That way we know that whenever we want to solve for the red vector, we have to use sine. And for the vertical vector, we have to solve using cosine. All right, so we're just going to scribble that in for our own reference, but it's not part of the official diagram. Yes, student.
Why is the friction not up 30 degrees to the left? Because isn't
Okay,
it?
here's the thing. As I'm dragging this across this way and pushing downwards, the box is still moving that way. Force of friction always opposes the direction of motion. Does that clarify your question? Remember, this thing is not going into the ground. You're
Does
implying the
that mean
force of
that
friction going to the
friction
ground.
will always
As I'm
be
pushing it this way,
negative?
friction is moving in the opposite direction. You guys might need to speak up because unfortunately I'm here in a basement, so I'm hearing all of the noises upstairs.
Does that mean that friction is always a negative?
Friction is always the opposite direction of the object's motion. That is always true.
Okay, so
We're
when
defining as
the
negative.
intended motion is positive, it is always negative.
We're treating as negative because we want to treat it as a scalar problem to simplify the problem. Again, in example number 1, I've shown the entire example using the scalar approach. Then I repeat it again using the vector approach. And as you can see, the vector approach, it does get rather messy in writing down the solution. All right, so that's why often we solve it as a scalar, because it cleans things up. There's less to write down and there's less to make mistakes on. On top of that, with regards to computer software, computers don't really know what vectors are. They only know scalar measurements. So you have to convert the vector world into a scalar world anyways in order for example, Excel to calculate out your measurements. Okay? In order for a computer to understand vectors, you have to write down this additional algorithm software for it to figure it out, but it doesn't matter. The computer will always calculate as a scalar anyways, so it needs to convert that vector measurement that's described to it. It needs to convert to a scalar first before it can do its calculations, and then convert back into a vector one more time. And that's just the reality of computers, okay, and how it's able to process information. All right, so that's why it's a good exercise to convert into scalar, because that's just how we're able to input information. All right, force of friction is left because, not because FH is to the right, but because the whole system is moving to the right. Remember, you can have a bunch of people fighting over this box. You can have big brother, big sister, little brother, little sister fighting against this. And the question is, who's winning? And you need to know those numbers. For example, if the people on the right are pushing with a force of, I don't know, 10 and 20 pounds, let's say, it doesn't matter, and the people on the right are only pushing with 2 and 3, we know that this box is going to move towards the left. And as the box moves to the left, the force of friction must be towards the right. Okay, so that's how you know what the force of friction is. You have to look at the problem itself and then establish your assumptions based upon the criterion given to you. And since in this situation over here, really you only have one person pushing against it, there's only one person to contend it against, so it's logical that the force of friction is left. Okay, that's how you get to the answer. Okay, the rest of this problem, I'm going to solve this using the scalar approach. All right, yes, you can do it vectorally, but let's just stick with the simplified version. Okay, as we know, we need to deal with the F net in our y dimension first. What is your question? All right, I heard something go up and then down. F net y is equal to 0. All right, and let's take a look at all of our y dimensions. Let me highlight it so you know. There's y here, there's a y here, and there's yet another y here. So there are 3 y values. FH is the force of the hand pushing on this. You can call it FA or FAPP for the force applied if you need to. Okay, so F net y is equal to 0 because of these 3 forces. The normal force, which is pointing upwards. The force of gravity, which is pointing downwards. And lastly, the force of the hand times the cosine of 30 degrees, which is also pointing downwards. That's where we get the plus and minus signs. In fact, if you want to write down a plus sign in front of Fn, just so that you know that that's why you chose it then that works as well. All right. Now we need to isolate for our normal force. Normal force is equal to all the terms brought over to the other side. So it's equal to Fg plus Fh times the cosine of 30 degrees. Fg is equal to mg. Again, we don't negate it because we've already done it at the beginning. So it's equal to mg plus Fh times the cosine of 30. And if you subbed in the values earlier, that's perfectly fine. So 2.0 kilograms times 9.81 meters per second squared, which has the same meaning as a Newton per kilogram. So I'll use that instead, plus the force of the hand of 5.0 newtons times the cosine of 30 degrees. So 19.62 plus 5 times the cosine of 30 will give us a value larger than before. All right, remember that our previous measurement was only 19.62. This time round is 23.95. Again, it's 23.95 because not only is gravity pushing down on the box, now you have somebody squeezing the box down even more. It's almost as if you have a box and you put a lovely transformers on top of it. You know the force of friction will increase because there's more weight pushing this down, forcing the molecules to get closer to each other, forcing their electrical bonds to become even more prevalent. All right. Again, scientists have noticed that the relationship of friction is based upon the normal force and the two surfaces. All right. So when the normal force increases, that's usually when you're squishing two objects together, the stickiness will increase. And that's what's going to happen here. Because with an increased normal force of 23.95, when we calculate our force of friction of 0.12, this answer will be higher than our previous answer. .87. I'll carry one extra sig fig because I've been keeping it in my calculator. Okay, so we know that our force of friction is 2.8 newtons towards the left. Now we can move on into the x dimension. Yes, students, what is your question?
I was wondering where you get the 0.12 from.
Oh, sorry, thank you. Oh, okay. I'm not going to edit this out of the video. Mistakes will just go in along with it. I forgot. I changed the question around. Why did I change the question around? Because if I use the previous value, you'll see the object get stuck. Okay. When you're pushing it at a diagonal after a certain critical angle, it's not going to move anymore. In fact, that's one of your homework questions. All right. What is the magical angle where it's never going to move? It's a double star question. So try it. I encourage you to try it because that way you have a better appreciation of all the crazy math that we're doing here. Okay, so yeah, in order for this experiment to still work, I had to use Teflon on top of Teflon. Okay, so yeah, let me just redo these calculations again. 2 times 9.81 plus 5 times the cosine of 30, that equals 23.95, multiplied by 0.04, and that gives us 0.958. 0.958 newtons. Okay, now onto the F net x dimension. If you want to skip a step, we know that F net is equal to MA. That is true. So your first line could be this, and there's nothing wrong with this. MA is equal to all of your horizontal forces. All right, so let's quickly see what our horizontal forces are, and there's only 2 of them. All right, there's the force of friction on the left, and then there is this component of the hand, which is moving on the right. All right, and that will be our formula. F net x, which is also equal to MA, is equal to force of the hand times the sine of 30 degrees, subtract the force of friction. All right. So acceleration is therefore going to be equal to the force of the hand, which is at 5.0 newtons, times the sine of 30 degrees, which will give us 2.5, by the way. So 2.5 subtract 0.958 gives us, roughly 1.5-ish. So our net force horizontally has now cut in almost in half. And our, our mass is 2 kilograms. All right, so go through that calculation. 2.5 subtract 0.958 in the numerator divided by 2 kilograms will give us a final acceleration of 0.77 meters per second squared. And let's vectorize everything. We know it's going to move towards the right, and there is our corresponding vector answer. And if we compare this answer here versus our original answer from yesterday, you can see how much havoc even the smallest amount of friction has on the outcome of an experiment. All right, so even Teflon on top of Teflon, even though the number may seem very small, we're only losing 4% in friction. That's it. But look how much your acceleration has dropped because of that minute amount of friction. And that's the reason why, with regards to most technology, we would rather have systems that are near frictionless. Like that famous toy that was around back 5 years ago. You know that thing where you spun it around like crazy? What did it have in the middle? Exactly. Ball bearings to reduce the coefficient of friction so that your fidget spinner can spin a whole lot longer. For tonight's homework, let me just erase all this stuff over here. All right, and here is all the PowerPointed version. Same answer anyways. All right, so for tonight's homework, finish off on course pack page 35. And that is it for today. Stop the recording now. Where's the stop button? It's somewhere. Take care. Bye now. Like, click, and subscribe.